Theoretical physics is a branch of physics that deals with the development of mathematical models and frameworks to explain and predict the behavior of the physical universe. Theoretical physicists use a variety of mathematical and conceptual tools to construct models and hypotheses that describe the fundamental laws of nature and the behavior of matter and energy at a wide range of scales, from the subatomic to the cosmological. Theoretical physicists often work in collaboration with experimental physicists, who perform experiments to test and validate their theories. Together, theoretical and experimental physicists work to advance our understanding of the fundamental laws of nature and to explore the mysteries of the universe. Without our understanding of the underlying mechanism of the nature, all kinds of today technology would be impossible. For examples, communication networking, global positioning system, GPS, high-performance computer and magnetic resonance imaging. The Institute for Fundamental Study, or IF in short, was officially inaugurated on March 14, 2011 by Naresuan University Council as a research center unit. From the first day to the present, IF members are working on the cutting-edge areas of research in theoretical physics to expand the boundaries of our understanding of the fundamental laws of nature, including cosmology, gravity, string theory, quantum information science, and mathematical physics. We would like to emphasize that frontier research in theoretical physics is essential for advancing our understanding of the universe and developing new technologies that would benefit not only Thailand but the world society.
Okay, good afternoon, everyone, and welcome to Tah Poe Seminar Series 56 and talk number 4. And today our speaker is Dr. Teeraparb Chantavat. And today he will tell us about extreme value modeling of the brightest galaxies at Z greater than 9. Please welcome our speaker.
Okay, thank you, Ajahn Parb. So I'm going to talk about the brightest galaxy at redshift greater than 9. Why is redshift 9? This is because it's the redshift that hasn't been observed, in large abundance by the Hubble Space Telescope and could be observed by the new JWST telescope. So this is like the new galaxy that's been observed beyond this kind of redshift. So I'm going to talk a little bit about the cosmic timeline. So what is our current understanding of the evolution of the universe, and talk about the JWST results, and also and next we'll talk about what I did in my work, especially on the luminosity function and the extreme value statistic, and then how would extreme value statistic tell us about the observed galaxy at redshift greater than 9, and some conclusions. Okay, so this is like the work that I've done in collaboration with Dr. Siri Chongchitnan, like in Warwick, and the detail of this talk is actually in this paper. So if you like to actually read more detail about it, but this is just like the summary of what in the paper. So this is the archive number. Okay, so this is like the current picture of like our universe. Okay, so we believe that Big Bang is the beginning of like everything, like matter and space time, and then at this time we got like the quark, gluon plasma, and then everything's kind of like coupled together. Okay, so we need some time, right, for the universe to expand and cool, so that different components will try to decouple and then become independent. And the problem is that we cannot observe anything, right, in this part because the photon is still coupled from the plasma. So we need a couple of time until the photon decouple and then we can observe it. So this would be the cosmic microwave background. Right? That the furthest distance we can observe using telescope. Okay? And like after that, like everything would be very dark, right? Because we don't have like any light emitting star. So it's going to take some time for the gravity to accumulate enough mass to actually start burning star. And people in the past, people have two scenarios for the structure formation. The first one is the top-down approach. Top-down is mean that we believe that the large structure form first. So that would be like the kind of proto-galaxy and then get fragmented to create smaller objects. Right? And the next scenario would be the bottom-up, which means that smaller object will form first and then aggregated to form like the bigger object. And at the moment, people believe that this would be the bottom-up approach, so that star would form first and then like aggregated until become galaxy and so on. So and of course, I mean, creation of star is very important because of like when the star exploded, we created heavy elements from the supernova. So that will eventually we got more metal and then more elements like we can observe in the present galaxy and stars. Okay, now so I'm going to talk about the JWST telescope. So this is like the next generations of the Hubble Space Telescope. So is expected to probe even further and like getting more data because of the larger aperture. The Hubble Space Telescope had aperture about 2 meters in diameter, but this one is about 6 meters, so it's got more like light collecting area and is operated in the near infrared regime. So this is when star got redshifted around redshift about 10 and 14 would observe in the near infrared, and that would be the main like channel for redshift for JWST. Okay, and the telescope was launched in December 2021, and it's been collecting the data for 3 years. Okay, so this is what been updated from the JWST. So as you can see, this the navy dot is the data from Hubble Space Telescope. Okay, and then the red dots are the data from JWST. So JWST get a lot more galaxies than Hubble Space Telescope. And then this one here, right? This was the furthest galaxy observed in 2000 2017, and it's been the champion for like a few years until JWST observed further galaxy. Okay, so the furthest galaxy that being spectroscopically confirmed at the moment is around redshift 14.2.3. Okay, so of course we got a lot more populations and we can analyze further. The lower panel, right? So this is the star formation rate density. So it tells us how much galaxy create star per unit time, per unit volume. So we have like a lot of data from the Hubble Space Telescope, and we have quite a concrete idea of what would be the shape of like the star formation rate density. But the problem is that this, with the new data, right, you can see that it's kind of beyond what people believed before. So this is something very exciting, right, that we have to observe why we see more star in like higher redshift than we expected from the low redshift data. And of course, I mean, if you like follow the news in the past 2 years, like some like people just claim that the discovery of JWST might eventually challenge the lambda CDM, and it's become a hype for quite some time. So so in this talk, like I'll tell you that we are going to stick to the lambda CDM. We're not going to challenge lambda CDM, but we try to see if the new result from JWST change our view on how the galaxy will evolve, right, to actually fit with the lambda CDM model. Okay, so so this is coming into my work. So the main ingredient that people classify or plot the distribution of galaxy is called the luminosity function. So it's going to tell us if you how many galaxies with certain brightness in a given volume. Okay, so and it's declining, right? When we talk about magnitude, the more negative it means the brighter the objects. Okay, so so this is the plot from like 10 years ago. So people believe that the Schechter model is like the fitting function for the luminosity functions because it's based on the spherical collapse model. So it's got some theoretical background that would be based on why it has this shape. So so it's going to have like the power law form, like for the like lower luminosity. Right? So this part here will be in the power law, and then and we have the exponential cutoff at some point. Okay, so that would make sense because the brighter the objects, the rarer the object that we can find. Okay, but the problem is that like this new data coming up again, right, and it's challenged the Schechter model that people believe for quite a long time. So I think the first guy who actually introduced the power law model is Bowler, right? That okay, we cannot use Schechter model to actually describe this point. So we going to use an empirical law that is the double power law model. So at the moment, like there are two competing like model for luminosity function, the Schechter model, right, and then the DPL or the double power law. So that's like 10 years ago. Now with JWST, right, people still like discuss whether or not we should fit the data using like these two models. And so this is the new result from Harikane. Right? This is at redshift 9. So it's both laws are actually fit pretty well. But if you actually go to a higher redshift, this one here, okay, redshift 12, you can see that the double power law actually fit better according to the new data. So now I think the community kind of shift that we should actually fit with the double power law model. Okay, and of course, I mean the problem is that these two model doesn't actually take into account of the star formation rate and also the star formation efficiency. Okay, so I'm going to talk about these two guys in a minute. So the star formation rate tell us how quick a galaxy produce star. Okay, so it's in unit of like stellar mass per year. That's the star formation rate. And the simplest model we can think of star formation rate is that we need some kind of accretion that drew the mass into the galaxy. Okay, so this is the halo mass, and this is how much it's like accreting the mass. And of course, like this mass will include the dark matter. So we only want the baryonic. So this going to be the baryonic fraction. Okay, so we only count the baryonic part, and not all the baryonic matter convert into star. So we have the star formation efficiency. This is the parameter in the model. Okay, now so this is the plot that show how we can plot the luminosity function with different star formation efficiency, right? So I think the black dot is from like Donald, right? 2024, and then the red dot from Harikane. So we have the Schechter and the DPL model, and then we have the model with varying star formation efficiency. And as you can see that I think all the model like consistent with star formation efficiency about 5%. Right? So this kind of fit with like 2 to 5%. Okay, so with this model we can conclude that okay, if we take it into account of how quick or how efficient the galaxy produce star, so the efficiency should be around 10 to 5%. That should fit with the data. Okay, so but the question still remain because first the luminosity functions model is actually the fitting functions that we try to extrapolate into higher redshift. So something that fits very well at lower redshift and then we extrapolate to higher redshift might not fit better, right? Because we take the data from this part here and then we okay, this should work, but this may not. And again, right, this is also related that the brightest galaxy that we observe will still be consistent with like the LF model, or we have some clue how we can modify it. And the methodology that we're going to approach, we use something we call the extreme value statistic. Okay, I'm going to talk a little bit about the extreme value theory. So the analogy is the central limit theorem. Okay, I think everyone know about this theorem. So so if we have the random variate, right, and then we all sum together, and then we find out what would be the distribution if we have infinite sum of all the random variate. It's going to approach the normal distribution. Okay, so this is the central limit theorem. And in analogy, if we have a lot of random variate, but we want to take the maximum of it, in the limit we have a lot more, what would the distribution look like. Okay. So fortunately, people have already answered this question. So it's become the Fisher-Tippett Gedanke theorem. Okay, so if we have like the cumulative distribution functions, right, and then we kind of multiply together, taking the limit, and then there should exist the non-degenerate cumulative function that when you take the limit of a lot of sample for the gx, and if you be in this form, right, after you do the proper like coordinate change, okay, and this has one parameter is called the extreme value index, and this extreme value index is quite important because it's going to tell us what kind of distribution your extreme value will look like. Okay, so so if it's like positive, it's called threshold distribution, and if it's zero, it's Gumbel distribution, and if it's negative, it's called a Weibull distribution. This is the shape of like this redistribution. Right? So in extreme value theory, the input that we need is actually the PDF or the CDF. Okay? We need to have some probability distribution functions as the input, and then we work out the GEV. Okay? It's for the generalized extreme value. There is another approach which is not related to this work, but the other approach is that we take the threshold that it cannot exist particular number. What would be the CDF of like the limit? Okay, but this work we take the GEV approach, and then we work out what would be the distribution of the extreme galaxy. I'm going to show you what the shape would look like first. So we predict that if we have the same observational capability as JWST, right, and the brightest object would be around here. Okay, so this is for star formation efficiency of like 0.02. And you can see that if we like increase star formation efficiency, you likely to observe brighter objects. Okay, okay, and at different redshift. And of course, I mean, our analysis show that the index is actually pretty close to zero, so it's fit well with the Gumbel distribution. Okay, so this is like the result of the EBS analysis. We will eventually get the distribution of the brightest object with some uncertainty. Okay, let's come back to the double power law model. So we collect a lot of like data, right? So it's not up to date, right? Because data change all the time. But at the time that we write the paper, we have like all the brightest galaxy, and then I think the black one will be the one that has been spectroscopically confirmed. So it's more believable. And the red points, they are like haven't yet have a follow-up spectroscopy confirmation. But that still be the basis of what we get. And the double power law model is very unphysical. Okay? Because like if you go to higher redshift, you expect to observe brighter objects, which is kind of counterintuitive. We think that if you go higher redshift, you should have like less bright objects. So this is not realistic. It's not surprising because this double power law is being fitted at lower redshift. Okay. So this model doesn't work basically. For the Schechter model, this is for the Schechter model with the same set of data. And you can see this one is better because it's more realistic, right? If you go to higher redshift, like the magnitude going to increase, so it's less and less, right? So that's kind of makes sense. But the problem is that we still observe this object that we confirm, but and still beyond the threshold of our IFTHEP. So again, right, we still think that this Schechter model still doesn't work. And the reason be the same because we did extrapolation. I think I'm already talked about this. So this is for the constant stellar efficiency model. Okay, so this is the same analysis, but with the model with star formation efficiency. And again, right, when you actually increase the efficiency, the bound kind of like getting lower, so you expect to see brighter objects, and it's realistic, okay, because it's curved up, and you can see that the data is actually consistent with star formation efficiency about 5%. And of course, 15% is still consistent, but for like conservative limit, we would say that 5% should be okay. Okay. Now, people think about the star formation efficiency because there is no reason for the star formation efficiency to be constant. Okay, because a lot of reasons. First, the halo mass is different because and then different halo mass have different accretion rate. So that will give you a different star formation rate and different efficiency. So people try to come up with the model that if we can actually vary how efficient the cluster produce star according to the mass. So that they come up with like some empirical model. And you can see that if you go to higher mass, the star formation efficiency increase because you got like more mass, more accretion rate. Okay, but it's not increased forever because once you produce more star, you got a lot more feedback, like the supernova feedback, and then the AGN, and the larger AGN, the more powerful the outflow, which will suppress star formation. So it's eventually drop. Okay, so in the literature we found two model, or it's the same equations but two different value of parameters from Tikela and then Halikane. Okay, so this is what it looked like when we like taking into account of how the star formation efficiency vary with the halo mass. And you can see that the Halikane model, right, is still not like the bound for like this kind of data, but it's still very, very close. So it's marginally pretty close to the data. And the Tikela model actually give the bound for all the observed galaxy. And one thing is that this EVS statistic can help us predict what would be the brightest magnitude that we can observe at higher redshift. So at the moment, if we assume absorption efficiency about 0.5, you would expect to observe this galaxy. Okay, now I think people, right, most people forget about Schechter model, okay, because is doesn't fit well, especially for the bright galaxy. So, but still believe that okay, we still have a very good empirical fit, especially for the double power law. So, Jonan actually revised the parameter and give the new set of parameter for the double power law model, and we analyze the new set of parameter, and it's all consistent with the data. So I think if you want a very quick empirical fit, that would be the most accurate one to use for the luminosity function. Okay, I'll come up with the conclusion. So in our work, we use the extreme value statistic, in particular the generalized extreme value, to actually identify whether or not different type of luminosity function work or not, or which one could be improved with based on the data from JWST. And the distribution of the brightest galaxy actually described by the Kumbel distribution. Okay, and previously all the double power law and the Schechter model failed to describe the galaxy observed by JWST. And for the constant stellar efficiency model, we believed that the efficiency should be around 5% to 10%. That will correspond to the observed data. And the model of varying SFE, right, they are actually okay at the moment because it still works with the data. And if you still like use a very simple fit, the modify double power law by Jonan is the way to go. And of course, I mean, in this work, we haven't taken into account of the cosmic variance and the Edison bias. The cosmic variance is that because JWST doesn't observe all galaxies, it's just only part of the sky. So there will be like variation of different parts of the sky that give the uncertainty. That's called the cosmic variance. And the Edison bias is the bias that people tend to observe brighter objects that it usually is. So basically, these two effects will have the effect of reduce the brightness of the extreme galaxy. Okay? And of course, we predict that if we can break the statistic, break the limit, like if we can observe like redshift at 16, the magnitude should be around this part. That is actually observable by JWST. Of course, I mean, in our group, we did a lot of like extreme value statistic application in astrophysics. We did analysis on the massive cluster of galaxy, and then the cosmic voids, and then the primordial black hole extreme, and then last year we did the massive population-free star, and then this work we worked on the galaxy, and we're currently working on the brightest AGN, which should come up soon. Thank you.
Okay, any questions?
Okay. The star formation rate depend on what physical quantity?
In the model is directly depend on the halo mass. So it's actually depend on the mass of the halo from this model.
The halo. You mean dark matter halo?
Dark matter halo, yes. But this is a very simple model, but in reality, we need to take into account of like the redshift feedback, supernova feedback, and then the outflow. So it's if we take out, it will be very complicated. But the simplest model is that it depends on the halo mass.
If the amount of dark matter in the halo mass is large, the star formation rate is large, right? Is
Say that again.
if the abundance of dark matter in the halo is high, the star formation rate is high or higher or lower.
It's,
It okay.
It usually increase with mass of the diameter halo up until certain point is going to drop. Okay, because like if we have like smaller halo, right? The larger halo you got more accreting rate. So if you draw a lot of like gas into the halo and it's produce star more efficiently, but at some point the negative feedback will kick in, right? We got like the supernova feedback and also the HN outflow that will suppress star formation. So it will increase up until about like 10 to 12 solar mass, and then it's dropped.
Next question. Do the people understand the process of star formation well? In your
We
opinion?
actually don't understand in detail. So people try to do the computer simulation, and then what we can do is try to get the empirical fit and then explain what would be the physical meaning of like the terms. It's very non-linear process, so we don't know in detail.
Okay. Okay. Thank you. Thank you.
Can you go back to slide number 6, please? For the the early time, they have only one star that observed.
So this is at redshift 6. So the Hubble Space Telescope observed a lot of galaxies like before redshift 6, but it's not included into this part. So we observe a few of them like from the Hubble Space Telescope, but that should be the very bright galaxy because that's kind of beyond limits of Hubble Space Telescope. But after JWST, we observe like a lot more.
I mean the earliest time, 290.
290.
Right?
Which one too? Oh, this
Yes.
one.
There are only one spot. That means they have only one star bounded by JWST.
This one is a galaxy. Is the what JWST observe? We use photometrics because it's very quick, and actually if you follow the news, like they claim that they go up about redshift 16, but once we redshift 16 is beyond. But once you actually do follow up, the spectroscopy is not at 16, it's about redshift 4. So so this one is both observed by photometrics and then follow up by spectroscopy, and it's confirmed that it's actually redshift 14.2. It's very old and is separated by 10 million years. Yes. Is Yes, it's pretty. It's very far away. Like if you like talk about like redshift, that is. So this one is the oldest, right? That I don't know is what was the oldest. Is good is the furthest galaxy. Yeah, but of course it's still exciting because we would expect to actually find like further redshift probably soon. And I like answer your question. Schechter model, yes.
Schechter model and double power law model. You said that the Schechter model is based on theoretical model, which is a
Spherical collapse.
spherical collapse. But what about the double power law model? Is it based on something or is it just empirical?
It's just purely empirical, so it doesn't have any theoretical ground. So that's why people try to stick with Schechter model for some time until we cannot do this anymore. Some typo the alpha this those are two different alpha. The main component of Schechter you have the power law and then exponential cutoff that's the different and also the amplitude. So this is like a 3-parameter model. But the double power law you got like one more parameter. The beta. I might check the model again, but this is approximately right. It should look something like this. You want to use the microphone? Sorry.
I mean, if I just treat the first term is leading order, and I feel the why you say the double power law model is the extension for previous model, but in this case, I feel the leading order is different.
It's the leading order is kind of a mix between like alpha and beta. It's kind of depend on the value of alpha and beta.
And because it's -1, so which means two models A are also different.
Oh yes. Yeah, I think I know your points. One of the term will dominate at low luminosity, and one other term will dominate at high luminosity.
Thank you.
I'm just curious about something about the ideas of top down and bottoms up. Do those ideas affect our perception about the universe? Let's say we want to observe at some redshift, at some point of redshift. Do the top down and bottoms up meet at the same point? I mean the data.
There are different scenario of structure formation, so they don't meet, right? Because the top-down approach, we think that large objects form first, so that would be like the proto galaxy that doesn't fragment yet, and then it starts to fragment it. So I don't think we can combine. You're gonna have like choose either one of the scenario.
I mean, those two can, I mean, do they observe the same, same process of galaxy formation? Let's say that we observe from this end for 1 point and the other end for 1 point. Do they meet at the same point?
Quick answer is no.
Okay.
Okay, more questions? No. Okay. I think it's about time to end the seminar and say thank you to our speaker.
Thank you. Like